So there's basically nothing new in this video. This is just a fun video for all of you. So we've talked about the power rule before, and when we introduced the power rule, I said it was for basically any exponent, even though technically at that point we could only prove it for integers. But the power rule works even if your exponent is a fraction, even if it's a rational exponent. And you use the power rule the same exact way. Bring down the exponent and subtract 1 from the exponent. Power rule is exactly the same, and it works for fractions, for rational exponents as well. And we're going to start by proving it. It's pretty easy, actually. I'm gonna phrase it as an example. Prove the above. Part A is going to be for m equals 1, and part B is going to be for any m. So if m equals 1, look at what we have. The derivative of x to the 1 over n. This is what we want to show. We can't use the power rule. That's what we're trying to prove. But what do we know about this function? This is f inverse for what function? Let's do exactly what we did in the last video. Well, to find the inverse function, that's going to be switch the x's and the y's. X equals y to the 1 over n. How do we solve for y? Raise both sides to the nth power. The left-hand side is x to the n. The right-hand side is n over n. Remember your properties. N divided by n is our new exponent. N divided by n is 1. So if f is x to the n, then this is f inverse. And we can use the inverse function theorem. These are inverse functions on their domains. And again, the domain really does matter because, for example, x squared, that's not 1 to 1. It doesn't have an inverse function. So you do have to restrict the domains on some of these. We're going to do a little hand waving, but there is domain restrictions happening right here. Inverse function theorem says this is going to be 1 divided by f prime of f inverse of x. And we can check that the inverse function theorem holds because, again, on our restricted domains, this is invertible and this is differentiable. And our denominator is not going to be equal to 0. That's going to be another assumption that we're going to be making. So there's a lot of things to be looking for, which is why I'm not technically calling this a proof. I'm calling it an exercise, even though I use the word proof. Yeah, looking at this. Well, again, what is f prime? F prime of x? Well, we can use the power rule. We did officially prove it. Well, I didn't prove it because it uses the binomial theorem. But there is a proof in an earlier section using material that we already know. So all we're doing is plugging in f inverse of x. And we said f inverse of x was x to the 1 over n. So f prime of f inverse of x, that's 1 over f prime of x to the 1 over n. What's f prime? F prime is this. So just take this and replace the x with x to the 1 over n. F prime is n times x to the n minus 1. That's what f prime is. We're replacing f prime with what it equals, but again, we're not evaluating it at x. We're evaluating it at x to the 1 over n. And now it's just a bit of a simplification game. Oops. I don't want this. Go away. I want it on the next page. There we go. Remember our properties. This is 1 over n. If you have an exponent to an exponent, you multiply the exponents. N minus 1 over n. Okay. I haven't proven this in a while. Where's this going? This is going to be 1 over n times x. How does this fraction simplify? N divided by n is 1, and then minus 1 over n. Okay. So what does this become? We could write it like this, right? 1 over n times 1 over the other one. That's fine. And then we can write that last one with a negative exponent. Making the negative exponent is 1 over n minus 1. And remember, whenever you're proving, if you're feeling lost, and I did this myself just now, you may not have caught it, but I definitely did. If you're ever lost in a proof, remember where you're trying to go. We were trying to prove it for m equals 1. We were trying to get to 1 over n times x to the 1 over n minus 1. That's exactly what we got. And then the part B proof is much easier. The derivative of x to the m over n, that's just the derivative of x to the 1 over n to the mth. We know how to find the derivative of the outside function. We know how to find the derivative of the inside function. We just proved it in A. So this is just a simple application of the chain rule. Derivative of the outside function is m. Subtract a power. Leave the inside alone. We're using the chain rule. And multiply by the derivative of the inside function, which we just proved in the last part. So we get m times, and again, we can simplify this as x to the m minus 1 over n, times the derivative that we just wrote, 1 over n times x to the 1 over n minus 1. And now it's just a little bit of housekeeping. This is all getting multiplied together, so we can multiply it in any order. This first part becomes m over n. In the second part, we just add the exponents together. This right here is m over n minus 1 over n, and we're adding this exponent. Plus 1 over n minus 1. Well, minus plus, they cancel out. And we get exactly what we wanted. M over n times x to the m over n minus 1. So the power rule truly does, not boxing it because that's not our answer. We're doing a proof. The answer is this whole thing. So again, writing these equal signs, having your work be organized is all very important. That's part of the answer. And yeah, we showed the power rule. And again, this only makes sense, when n is not equal to 0. On the domains of these functions, October, don't you scratch up my new chair. October, no. Okay, so we're going to do one more example, and then we'll move on to trig. I know everyone really, really likes trig. So we got that coming up for you guys. Gotta find my pen again. Oh no, I'm blurry. All right, I'm clear again. All right, example 3. Let's see what October does. Find an equation for the tangent line to y equals x to the 2/3 at x equals 8. All this wants you to do is use the power rule. You could use the inverse function rule, but then you're also still going to have to use the power rule. Inverse function theorem. So power rule says that the derivative, bring the exponent down, subtract 1 from the exponent. Oh, it's 2/3 minus 1. That's 2/3 minus 3/3, or negative 1/3. And again, if you wanted to, you could write it like this, with negative exponents becoming positive exponents. 2 divided by 3 times the cubed root of x. So the equation of the tangent line is y minus the y value equals the slope times x minus the x value, which is 8. We don't know the y value. We can plug in x equals 8 to get the y value. That's the cubed root of 8 squared, the denominator becomes the index of the radical. Cubed root of 8 is 2. 2 squared is 4. That's our y value. And the derivative here, when x is equal to 8, is 2 divided by 3 times the cubed root of 8. 2 divided by 3 times 2, or 1/3. So this should be the equation of our tangent line. And anytime you get an equation of a tangent line, you're going to be checking your answer because it's that easy with technology. And it's cool to see. All right, x to the 2/3 power. Ooh, that's a funny looking function. And our equation of our tangent line is going to be y minus 4 equals the slope, which we said was 1/3, I think, x minus 8. And look at that right there. It is indeed the 0.84. That is indeed a tangent line. And again, look at our derivative. What's the domain of our derivative? What's the domain of our slope function? This slope function is defined anywhere except when x is equal to 0. That causes us to divide by 0. Remember, cubed roots, take in negatives, no problem. Negatives aren't a problem for odd indices. But we can't find the derivative at 0. There's two reasons for that. One, the limit from the left is different from the limit from the right. And two, each one of these goes off to infinity. These each have one type of vertical tangent line. Vertical tangent line is also undefined for a derivative. It's an infinite slope, basically. The two reasons why the derivative at this point does not make sense. Anytime you have a sharp edge like this is technically called a cusp, C-U-S-P. The derivative will not exist right there. Okay, that's it for this video. Let me know if you have any questions, and bye-bye.